Hey everyone, thank you for being here on time. It's 6 p.m. We have a lot to cover, but I do want to wait at least like 3 extra minutes just for people to trickle in because that always happens. So we'll get started right around 6:03. Just make sure that you sign in with the attendance form while we're waiting. And we'll start in about 3 minutes.
Hey, how's it going, everyone? My name is Zane.
All right, it is 6:03. There's too much content to wait all 5 or 10 minutes. So let us jump into things here. Please make sure to go ahead and fill out this attendance form really quick. I'll leave this up here for about 10 seconds, but you can also go to this tiny URL here, the UCF Discord. This just helps us track what events were popular, worth running, who was there, and helps us gauge feedback for what the event turnout was. So please go ahead and make sure to fill this out. I think it might be on the last slide as well, but don't quote me on that. Cool. Thank you everyone for being here. We are here to talk about strategies for solving practice questions and strategies that you can use to solve new questions in a technical interview or an online assessments. So we'll be doing a bunch of practice today with some sample questions that Zane and I have picked out, do some review of some important data structures, and then more importantly, define a framework of strategies that you can use to identify what's important and hopefully come up with a solution that works for that problem. So we'll have, I think, 6 different problems that we'll go through today, get through as many as we can. But if we don't get through all of them, then all the solutions will be available afterwards, and we'll have a link for that very shortly. All right, quick introduction. My name is Eli. I'm one of the tech leads here at the Google Developer Student Club. I am a senior right now, going to graduate in May of 2023. Zane, why don't you go ahead and introduce yourself really quick?
Sure. I'm also tech lead at the Google Student Developer Club. I'm a junior. I'm graduating next year as well in the fall. And yeah, I'm hoping to be able to help you guys out today.
Awesome. All right, so really quick event structure of what we're going to do. We're going to start by introducing all the strategies, some important things to look for when you approach a new computational question. And after that, we're going to jump straight into the thick of things. So we're going to go one data structure at a time, cover the important details of that data structure. And once we do that, tackle a couple of Leetcode questions pertaining to that particular data structure and have an opportunity to actually apply those strategies. And everything we're doing today is going to be in Python. Python is a very popular interviewing language. If you're not super comfortable in Python, hopefully you'll have a better grasp of the syntax by the end of this, but you are absolutely welcome to go ahead and do this and follow along in any language that you want. Personally, up until this point, I've done all of my programming interviews and practice questions in Java. It's just some extra boilerplate, so you can do whatever you want. Awesome. So without wasting any more time, we've broken down our strategies into 3 different slides here. And the most important thing to keep in mind when you are looking at a new problem is that cheating yourself is not going to be helpful here. So I'm going to go ahead and show you what I mean really quick by split screening with Leetcode. We'll go ahead and pull this off to the side here. And if I go into a random problem, let's say I decided that I wanted to try and solve. There was a really good one in here, but I don't remember exactly which one it was. I think it was this, search and rotated sorted array. Yeah, this is the one I wanted. So you'll notice that there's a lot of information in here that you would not get if this were an online assessment or an actual interview question. Like there's tabs at the bottom for related topics, similar questions. If I know that a related topic to this problem is a binary search, then I'm probably going to think about how I can use a binary search to solve this problem. But an interviewer isn't going to tell you that, and you need to be able to make that conclusion yourself. So opening things, looking at information that is not available during the actual crunch time where it's important is cheating yourself, and it's not going to be helpful for when you're going through an actual interview. So resist the temptation to look at all of this, discussion posts, submissions, anything like that. Another thing that's really important is to make sure that you finish reading before you start jumping around to other information. It's very easy to maybe get through like half of the problem description and then notice something important that you want to double check with either some example test cases or with the constraints. And jumping around makes it hard to come back and regain the same thought that you had. Maybe it means that you're going to come back and you skip a line by accident, or something that you were thinking about kind of gets put on the back burner and then never comes back to forethought. And making sure that you actually go through and get all the information before you start considering more information is something that's really important to make sure that you don't miss anything. And similarly, making sure that you're rereading important details is also really, really important. There's usually a couple of sentences or important details in a problem statement that if you gloss over them, if you jump around and miss them, then you're solving a completely different problem. For instance, in this one that I pulled up here, there's one line at the very end that says this algorithm has to be solved in log of n runtime complexity. If you ran a very simple search on this problem through the entire array that is the input, it would totally work, but you'd be solving the problem incorrectly. And so making sure that you have all the important details in your head is something really important to do before you even get started on any. And then finally, for this first slide here, it's also really important to make sure that after you run through all of your all of the details of the problem, that you actually run a quick simulation or a couple, just to make sure that you understand what the underlying process is. So you'll often get some example test cases here, but there's no work involved. And so making sure that you can go through by hand, if you have a scratch piece of paper and a pencil, or if you want to do it like on a virtual whiteboard, just running through to make sure that you understand the process of going through and solving the problem by hand is really important to make sure that you're going to come up with solutions that's the right thing. It also might give you a head start about thinking what you actually need to do in order to solve that problem. Maybe you're going through by hand and make a key observation, something that's really important. All right, that is a lot of strategies, but there's a lot more where that came from. The next step after you go through and you've looked
I think he did freeze. Can you guys hear me as well?
But there might be like one constraint or one thing that you come across that, well, I don't know how I could do this efficiently. And the underlying challenge is coming up with a data structure and algorithm that actually does that. There's a couple of questions here.
Yeah, you kind of cut out for a little bit.
All right, I'm sorry. I got the notification that my internet is unstable. So if that happens again, please just let me know. Was there anything important that got missed?
We only heard up until the part where you had mentioned like, maybe there's one constraint that might help you solve the problem. It was for like 15 seconds or so.
Okay. So you might be missing, there might be some constraint that's a problem, or maybe there's one particular computational thing that you can't do efficiently. And trying to figure out what data structure, what algorithm is going to help you do that is the underlying problem that you're trying to solve. So figuring out what that challenge is in advance is really important. And sort of in that same vein, coming up with important or dangerous test cases is also really important. You'll usually get a couple of example test cases, but the test cases that they give you are never going to be ones that are like really challenging or things they're going to like run the tests to make sure that you actually solve it correctly with. So maybe a test case where there's no input or the input is invalid if that's possible. Coming up with those test cases on your own to make sure that your solution, when you come up with it, is going to behave correctly with those test cases, making sure that you understand how those test cases need to behave in case that changes the behavior of your program is something important to do at the very start. And then after that, another thing that's really important is just, there's usually an easy solution. Start with the easy solution and then iterate from there. Maybe the easy solution is you understand almost the entire problem, but then there's one particular part that you can't figure out how to do efficiently. Well, we can think about ways that that challenge that we identified could be abated. Maybe we need to save some data somewhere. What kind of data structure? And for our last section of strategy.
Okay. Can you go on to the next slide? So we can just keep, okay, there we go. So in terms of more strategies, so one of the things that I always try to look at or just always know are the constraints of the problem. So if you go to any Leetcode problem, once you scroll down on the left panel past the different example cases that they might have, the actual description of the problem and all that sort of information, you have the constraints at the bottom. And typically they can give you information such as how many elements you might be given in an array or just in a collection of items, or what some values might fall within in terms of a range. So maybe the values fall from -10 to +10 only. Sometimes the length of an array might go up until 10 to the 5th. So you should always read these problem constraints, because then you can easily cut out or not even consider certain solutions or certain runtimes. So you can use some simple math to what I call like calculate the minimum viable runtime. So that's just kind of telling you, okay, there's no way it's going to work if I do an n squared solution or n cubed solution. Hopefully you're not doing that. But you can kind of use some simple math to evaluate that. So for example, if you have an array or a question that might give you at most 10 to the 5 elements, so 100,000 elements, then you know for sure that n squared is not an option, because if you take 10 to the 5 elements and you square it, you're going to have 10 billion iterations, which is way too slow. So right out the gate, that is too much. Meanwhile, you might be able to get by with an O of n solution, well, which normally will be good depending on what the problem's asking for. Another example is if you're given maybe 8 elements, then you can get by with a 2 to the n, so 2 to the n solution, or an n factorial solution maybe, because 2 to the 8th is 256, which is a small number, and even 40,320, which is 8 factorial, is not as large of a number. Typically, you can get by as long as you're under 10 million. From what I've seen, once you start going into 100 million, that's where you're kind of cutting it close. But for the most part, you can use certain problems and their constraints to
It's
kind
just
of
something related
cut
to
out some solutions.
coding.
Sorry? Hey, did you have a question?
I think someone was just unmuted.
Oh, okay.
It happens.
Yeah, so that just kind of wraps up that part of it. Definitely look at your constraints because they can give away the possible solution you might end up going on.
All right. So the next thing on here that I just want to introduce you to really quick is an extension that Zane had mentioned. It's available in the Chrome Web Store. If you go over here, chrome.google.com/web store, and then look for Leetcode Enhancer. So this is an extension that will allow you to hide some information on the Leetcode homepage when you're browsing for a new problem that can help you to focus on specifically like, the problem that you're looking at and hide information that maybe would tell you in advance before you decide to solve this problem what would be helpful. So you can hide difficulty count, solve problems, all kinds of things in here. This is something you could definitely play around with if you're interested in running like dedicated Leetcode practice sessions or something like that.
Just to
We're not
mention
going to
real quick on that is the reason you might want to use that is if you see an acceptance rate of 30%, you might be like, oh, I might not be able to solve this. When it comes to the category of a question, so part of the problems with getting good at these technical interviews or Leetcode in general is identifying what pattern, solution, or maybe what algorithm you might have to use. And if you get the category like binary tree or maybe graph, dynamic programming, whatever it is, that might already kind of give you a mind frame of how to think about the problem. But you have to develop that because in an interview, they're not going to tell you, hey, this is a dynamic programming problem. So that's kind of why I use that, just to touch up on that.
Yeah, this fits under the category of don't let yourself cheat, information that you wouldn't have during an interview. Awesome. So with that, we're going to get into the main content of the presentation today. We're going to get through as much of this as possible. I will pass it off to Zane at 7 o'clock at the latest. So we'll all get through hopefully 2 problems, 3 if we're lucky, but I'm not 100% sure. But we'll definitely get through at least the 2, and then we'll get into some more advanced data structures from there. All right, so with that all being said, I'm going to see if I can figure out how to make a whiteboard on Zoom.
There's Microsoft Whiteboard if you want to use that.
I think that I may have to, because I don't see anything about a whiteboard on here. All right, so here we are. We're going to go through and review what a linked list is for anyone who's here who's in the middle of CS1 or before and hasn't fully experienced linked lists, or people that have been around for a while but just need a refresher. Just make sure everyone's on the same page first. So this is our first data structure that we're going to cover. And a linked list is a collection of nodes, which we're going to represent with a circle. And each node has a value in it, and it has a reference to either a node that occurs before it or a node that occurs after. And which one depends on the structure of our list. Typically, what we'll do is we'll have a bunch of nodes that point in a row to each other. I'm doing a great job here. And we'll have a head of our list, which is the very first element, and we'll have a tail of our list. So the reason why we would want to use a linked list, let's say there's data in here 1, 2, and 4. The other type of list that we could potentially use would be an array being just a collection of boxes that are indexed. And then we can figure out what's in the ith box very quickly. why we'd want to use a linked list over an array is flexibility of adding to the front and the back and dealing with stuff in the middle with constant time operations. So let's say I wanted to add something onto the end of the tail here. All we'd have to do is create our new node. Let's say this is -1. We could just create a new node object and we can grab our reference to our tail and just point it directly over here and then update our tail. So we just did like, arbitrarily like 3 operations or so. That was a very quick thing to do, constant time. We didn't have to do anything special. In an array, this wouldn't be anything crazy either. We could just put something in the next box, but it gets a little bit more complicated if we want to do something in the middle. With a linked list, let's say we want to take out this element here. Well, all we have to do is we have to get the element in front of it and update its pointer to go straight across. And this can also be done in constant time. The difference here is that an array, if we wanted to take out this element, we would have to shift everything afterwards up 1 box in order to make sure that our array is still contiguous. So anytime that we have something where we want to take stuff out in the middle, or having links is a little bit more useful than if we don't like directly need to index our list, then having a linked list is really useful. And we can also do a bunch of different things with our linked list. We can make a couple of design decisions about how we want it to behave. What we did in this over here is we had a singularly linked list, which means each node points in one direction in the list and all of the nodes point in that same direction. And then we have a head and a tail. We can also make a doubly linked list, which means each one points both ways. And that way we can actually traverse in both directions of the list if we want to. We can go to the left, we can go to the right. And that way, if we start from some arbitrary node, we can easily get to the node in front of it and the node behind it. Whereas over here, if we just started at this node, we'd have no way of knowing what's in front of it. So sometimes this is useful if the specific application demands it. We'll actually cover a problem where a doubly linked list is helpful. It's one of the ones that I'm not sure if we're going to get to, but theoretically we could. And the other thing that we could do here if we wanted to is we could also circularly link our list, which means that the front goes to the end. Let's say this is still head and tail. In this case, if we wanted to do this, we don't actually need a reference to the head and the tail because we can always find the tail as whatever is in front of the head by going around our big link at the end. So there's a couple of design decisions here if this is something that you feel like helps solve the problem that you're working on. Okay, so that is a very quick recap on linked lists. And now we're going to jump into an example problem as a group to see if we can figure out how linked lists work. All right, so I'm going to go into Leetcode here. Everyone should do the exact same thing. We're going to open the problem palindrome linked list. And I'll give everyone about a minute to do so. Go ahead and close down this old one here. I don't need my OneDrive. Can you please close? Thank you. And I will go ahead and open up this notepad here, where we have collected a summary of the framework that we established for going through this problem. It's not as important for this particular problem because it literally tells us what the data structure we're using is. It's a linked list, like we don't have to figure out what's the data structure, but there are some underlying challenges here that I think would be really helpful to go through this framework in order. So let's start from the beginning. Let's go ahead and read the problem here. The problem is very simple. We are given a linked list just by the head elements. Go ahead and clear this out for a second. We are given a linked list only by the head, and we have to determine if it is a palindrome. And the example test cases here say that if we split this one in half, it's 1, 2, 2, 1, which is great. This one is 1, 2, which is not a palindrome. So We've read the problem. We have some important information. Anyone have anything that they think is like really important here that they picked out? Yes, we can zoom in a little bit. Anything in here that maybe I glossed over, anything that's really important that we need to note before we jump into this? Audience participation requested. You can use the chat, you can unmute, whatever you want. All right, I will go ahead and start with the first thing. What I did not mention to you guys down here was there is a request here in order to do it in a specific time and space complexity. So we need to try and think about a way that we could do this in O of n time, which means we only go through our linked list in linear time complexity. We could do it multiple times if we want to, but we can't do it like in n squared complexity. And the more important constraint here is we can't use a linear amount of space. We can't create another list. We can't create something that is the same amount of elements. We need to do it with constant space. So I will go ahead and assume there's no other important information that anyone has picked out here. Let's go ahead and review the constraints for a second. So the number of nodes goes up to 10 to the 5th, which means this could be very long. So this O of n time complexity is going to be important. We need to try and keep it there as much as possible. If we do O of n squared, it could be way too long. And the other constraint is that the node value is a single digit, so we don't have to worry about multiple digits influencing our palindrome, which means that if we see the exact same nodes in the same order from head to tail, then it's a palindrome. There's no case where something could be multiple digits and it would still be a palindrome. Like this would be 1 to 2, 0 to 1. That would be a palindrome, but the nodes aren't exactly the same. So what is the underlying challenge here? This one, I do want someone to tell me. What do you think about this makes it hard? Keeping in mind this O of 1 space complexity. It's going to be a really long event.
A hint might be the structure, guys. The structure of a linked list, no.
So let's think about this. Let's go on to the next step and let's start with our easy approach. What would be an easy approach for this? Well, an easy approach would be, let's just store this in a better data structure that we can just reverse really easily and then see if it's the same thing. So one approach that we could do would be to write all of the digits that we find in order to be a string and then reverse the string and then compare the two. That would be pretty simple. That would go ahead and solve our problem. It would be O of n time complexity. And we could do that very easily. We could actually do that right now just to prove that it works. So string str is equal to empty string, and then while head not equal to none, str plus equals head dot val. So I'm taking this definition of our individual node here, where each object has a value property and then next, which references the next node. And then head is equal to head dot next. And then return str is equal to str. This is syntax for reversing a string. This is not super important. Just realizing this is not going to work. So if we run this, this theoretically should work pretty easily. And it does. And we could do this with more complicated things here. And make sure this works as well. So this is fine. The solution definitely works, but is this O of 1 space complexity? The answer here is no, because we are creating a string of length n and then reversing it, creating another one. And so our space complexity here is linear. So we need to find a way that we can solve this problem without creating anything new. And one suggestion here would be that we could do this by reversing the order of maybe some of the links. Let's say that this linked list right now only goes in one direction. Well, if we had a reference to the tail and we inverted the direction of these back elements, well, then we could just iterate at the same time. So if we started from the head and the tail, we could say 1 is equal to 1, okay, 2 is equal to 2, okay, nothing, and then we end. And so that's where our solution here is going to come from. We want to find a way to reverse the back half of the list and then iterate at the same time and compare nodes. And that way we don't have to create anything new. We are working with the same nodes that we had. All we're doing is changing the references. So constraints, we already did that. Important, dangerous test cases. There's not really anything to be aware of because every linked list will be at least the size of 1. But we can think about this a little bit more in the future. Okay, so let's lay out what we want to do here before we jump into the middle of things. So we want to reverse the back half of the list, starting from head and tail at the same time. Compare nodes. And then we'll return true if they all compare to be the same thing. So let's figure out how we could do this. In order to reverse only the back half of the list, we're going to use something called a two-pointer approach. I think there's probably other names for it as well, but this is something you can do, especially with linked lists or with arrays. And essentially what we'll do is we'll have one pointer that moves 2 nodes at a time and one that only moves 1 at a time, so that the node that moves less nodes essentially moves half as fast. And when the one that moves twice as fast gets the end, then we know that the other one is exactly in the middle of our linked list. So if we start them both from 1, pointer 1 will be here, pointer 2 will be here, and then we'll know that we can't move it twice again, so we only move it to the end. And then we have a node here and a node here, and that'll be our halfway point. And once we have that, we now have a reference to the very end of our list, which we want to hold on to. We want to keep that. And then we also have a reference to essentially the starting point of the back of our half of our list. And from there, we can go ahead and reverse all of the nodes that we have up until the end. So let's break this down further into steps, just to make sure that we know what we're doing here. Start 2 pointers and move them through the list, starting from reverse back half of list with lagging pointer, iterate with head and leading pointer in opposite directions. And when I say lagging and leading, the lagging pointer is the one that's only moving 1 at a time, the leading one is moving 2 at a time. So with that being said, let's evaluate this. Is it going to be O of n time complexity? The answer is going to be yes, because we're just going to be moving through the linked list once to go through, and then we'll be moving through it a couple more times, but we're not moving through it like n squared times or n cubed or any crazy operation. And we're not creating any extra space. Our pointers are already there. We're just creating like individual variables, which counts as constant space. So this works. Theoretically, shouldn't run into any issues with our constraints here. So let's go ahead and start writing this. So we'll create a leading pointer and a lagging pointer, and they will both be set to the head value. And if you guys are screaming internally, I'm not a Python person, so if I'm not doing perfect syntax, you can either let me know or just keep it internally. So we have our leading and our lagging pointer, and let us figure out how far we can make them go. Leading is equal to leading.next.next, which means we're going to go to 2 nodes further. Lagging is equal to lagging.next. And how do we know when we can stop? So in this case, the thing that's going to be potentially an issue is that this node over here doesn't have anything it's pointing to next. That next value is going to be null or none in the case of Python. So we don't want our leading pointer to try and go to the next node or the next node, and one of them is null, which is going to throw an error. So if leading.next is equal to null, that's a problem. Or none in this case. Or leading.next equal to none. So in this case, if our leading pointer was right here, leading.next exists, leading.next does not exist. So we don't actually want it to stop here. I think I led you guys astray. Let's try this instead. Actually, no, I was right. So here's what we're going to do. If leading.next is none, that means we got to the very end of our list. If leading.next is none, that means we're at the second to last element. And let's think about why we might stop there. In this list, when we move twice, that puts us here. If we move twice again, it doesn't work. So an even length list will end us 2 from the end. If this was an odd length, let's say this 1 doesn't exist, 1, 2, 1, 2 doesn't work, but we're at the end of our list. So it is potentially that we might stop here. If that is the case, we just want to move to the very last node so that regardless, leading is going to be at the end. And our lagging will always be, in the case of an even list, our lagging just moved once, which means it's the node before the split. And if this is an odd length, then it's the node right at the split. So in this case, our leading would have moved 2 to the end, lagging would have moved 1, which is right in the middle. So what we want to do is we want to take everything in the second half of our list and we want to point it backwards. So this is going to point here, it's going to point here, it's going to point here, so on and so forth. And we want to take whatever this is and point it to nothing. We want to break it in half. We want to be able to iterate from front to the middle and back to the middle, but we don't want to go through the whole list again. So when we're reversing the back of our list, what we're going to do is we're going to take whatever our current lagging pointer is, get the next thing, point it backwards, and then move on and move our lagging pointer to the next thing. So we're going to do this a couple of ways. Well, lagging.next is not equal to none. While lagging is not equal to none, we are going to so let's think about what could potentially be an issue here. If our lagging pointer was on this node right here, this 2, if we went ahead and immediately said this one.next is equal to this, then we're going to have an issue because we now lose access to this one over here. And so we need to make sure that we're not losing our ordering and making sure that we can actually go through the list in completion. So let's think about how we can do this. Say our list is 3, 5, 1, 2, 7, 3, 5, 1, 7. In this case, our lagging and our leading in this case, lagging and our leading. So here we want both of them to converge on this one, or none of them. That would be fine too. So what we're going to do is we're going to get this next element, point it backwards, save a reference to this, and we'll be good. And then in this case, we'll have our lagging. We'll get the next element, point it backwards. And we'll be good. So in this case, neither of them should converge. All right, let's test this out and see how this works. So we're going to temporarily store lagging.next. We don't know that lagging.next is valid, but only lagging.next. And let's set okay, so what's the problem here? Let's do this. Let's grab a reference to our previous pointer, which is currently nothing. In this case, we want our lagging pointer here to point to nothing. In this case, we want this to point to nothing for its next value. So that's fine to just go ahead and do lagging dot next is equal to previous, lagging previous equal to lagging. So here's what we did. We went through a couple steps. So we took our lagging pointer, pointed it back to our previous element, which in this case starts as none, but in the next case it'll be 1, then 2, then 7. So we pointed our lagging pointer backwards to the previous thing. And then we just went ahead and updated our previous, and we also updated lagging. So now lagging will be here, and previous will be here. And we point this one back, then we point this one back, and that'll go ahead and work. All right, so we did that. And our last step here is that we need to just go through and iterate and make sure that everything works. So let's do, right now we have our head, which still points to the front of the list because we never changed it. And we have our leading pointer, which is the tail. So while self.head in the case of a JavaScript object, oh, never mind. We just have a reference to head. So while head is not equal to none, and lagging is not equal to none. Just compare the value. If they are not equal, then we return false. I think this works. And then at the very end, if this all fails, we'll return true. And we need to update our head and our leading pointer. And if either of them runs into nothing, then we'll know that we have terminated our list and it is okay. There should be no case where maybe like head runs into nothing really early and there's still a bunch more things in lagging just because of the way that our code works. All right. Let us go ahead and see if this works for our current test case. So this is a palindrome that we created down here. And it does not. So let's figure out what we did wrong here. Okay. So we have some other issues here, not equal to, yep, you're right there. All right, so there's some more serious issues going on here. But it's already 6:45, and I don't really want to spend any more time on this problem. So this is a case of where debugging would be really useful, or to try and solve these and figure out what's going on. But if I spend any more time on this, then we're not going to have any time to cover anything else. So the full solution for this problem is available on our GitHub, which is the very end. So we'll show that at some point. But there's probably something that I need to change in here in order to get it work. Debugging is a totally normal process. I think the approach is solid, and as long as your approach is solid, that's what's going to be most important, even if it doesn't perfectly work. Okay, so with that being said, let us briefly cover the difference between stacks and queues, and then we'll solve one more problem, and then I'll pass it off to Zane. So go ahead and refresh here. Great. So we can organize our linked list into a couple different things. We can organize it into a stack, which means that our nodes are ordered in such a way that we put things into it on top. So this is the top of our stack here. So we would add something new on top and link it up. And we also remove from the top as well. It's the classic last in, first out approach, which I'm sure that you've heard about over and over again if you've taken CS1. And a queue is the other way around. We'll put something in, and then we'll add another thing and link it downwards. And we insert to the back of our list. So this is the tail of our list, and this is the head of our list. And we always remove from the front if it's a queue, and we append to the back, whereas a stack, we append and we remove from the top. And the reason why you might notice a difference here is really just like what it can do in terms of application. So in the case of a stack, if you have something that requires getting the most recent value that you've stored, then a stack is really important. Whereas if you have something that's related to priority or something that's been in there the longest is the first thing that you want to deal with, or you just want to sequence things in order, then generally a queue is going to be your preferred approach over a stack. And it's not the case where every single problem is going to require a stack or a queue. Maybe one just requires a standard linked list with some modifications, but these are versions of linked lists that can be really useful for solving specific problems. And the one we're going to try and solve here, I'm going to leave the least recently used cache out because you could spend a whole day trying to solve that. But what we're going to solve here is we're going to solve daily temperatures. And I'm not going to tell you what data structure to use. This one is really helpful because it doesn't give you any hints, and we're not going to give ourselves any hints. But we're going to see if we can find a good way to solve this problem. So going back to our framework here, first thing, we got to read the problem. So we have an integer array of temperatures. Each temperature is the number of days that you have to wait until you get a warmer temperature. That's what we're outputting. And if there is no future day that's warmer, then we'll output 0 in that place instead. So if we go here and just validate what that means, 73, the next warmest day is literally the next day. So we would just have 1. 74, again, 1. 75, there's no warmer day until 76, which is 1, 2, 3, 4 days later, hence our 4. And at the end here, 76, there's no warmer temperature. 73, there's no warmer temperature. Okay, so with that in mind, we have reread for important information. Things like, put a 0 in if there is no warmer day. Something we might have noticed is that at the very end of our list, there's never a warmer day, so that will just always be 0. And then reviewing constraints. This is another case where the numbers are going to get really big, the individual temperatures, but that's not really something we're worried about. We're more worried about the number of elements rather than like the size of the elements themselves, because we're not like doing any addition or multiplication or anything here. So we're not worried about like a stack overflow. In this case, the number of temperatures is only up to 100. So like maybe that means that we could get away with not that great of a solution. Like if we made an n squared approach that theoretically could be okay since there's not a whole lot of temperatures. Can someone outline for me really quick what an n squared approach to this would look like? Someone unmute for a second. Yeah, exactly right. So an n squared approach here would be, we go through the array in order, we select one at a time, and then we go through the array again, everything afterwards, and just goes until we find temperature that's warmer. So 73, we would iterate through the whole thing and stop at 74, so on and so forth. And that would be fine. We could actually write that up really, really quickly here. Let's go ahead and do that. Let's create a result array, which we're going to do some syntax here. So we're going to create an array of all zeros, and the length is going to be the length of temperatures. And then for I range and temperatures. For j in range, I plus 1 temperatures. If temperatures j is greater than temperatures
He just didn't do it.
I,
Outreach. Oh, actually, that's 84.
Yeah.
then res of I would be j minus I, so number of days. And then we can just return res here. We can go ahead and run this and see if this works. This does not. Do I just not understand how a range works? Like the temperatures. All right, just to make this easier. All right, this is a demonstration of the fact that I haven't used Python in a while. But we could fix this range loop so that it actually starts from I plus 1. And then at that point, it would go ahead and work. But we can potentially come up with a better solution. So let's think about what ways that we could solve this with other than n squared approach. So curious if anyone has any ideas, just throw them out. But we're just going to kind of talk through this for a second. If we're going to arbitrarily say, let's look at temperature 71 here, how would we what ways could we figure out when the next warmer temperature is if we just wanted to go through here linearly? Well, what we could do is we could go and we could keep this here. And once we get to 72, we can backtrack and say this one, it's warmer than these two. So we're going to update these values. And then do the same thing here, look back a little bit. But we don't know how far we would have to look back. It could be up to n elements, which means that would be another n squared approach. But what if we traded some space or save some time complexity here? Thinking in the vein of stacks and queues, is there one that we could use here to potentially make this run a little faster? Why do you think that a stack might work? All right, I respect the guess. So one thing that we could do is we could essentially, like the key thing to note here is that in the question, it kind of like tells us a little bit of a hint that a stack might be useful, because we want the next available, like we want to, for each warmer temperature, we want to find the closest option, which means that we could put our days onto a stack that says these are unresolved days. I don't know when the next warmer temperature is. As soon as we get to one, sorry, I have a sore throat. As soon as we get to one, we can look back on our stack and say, well, the thing on top is cooler, which means that this temperature resolves what's on the top of our stack. And we can solve that. We can pop it off. And we can do the same thing with the next thing below it. If the temperature also resolves that, then great. So let's say we had our stack of this sample test case here, starting at 75, because that one will get unresolved. So we add 75 since we don't know what to do with it. And then 71, we could go ahead and look at the top of our stack and say, well, that doesn't work. So let's just put that on as well. 69, that doesn't resolve. So let's go ahead and put this on as well. And you'll notice that as we add things to the stack, if they don't resolve what's on top, then our stack is going to be strictly decreasing from bottom to top. So if we find something that is actually higher, now we get to our 72 here. Our 72, we could look at this and say, well, 72 is warmer. So now we actually know what to do with this 69 here. We can go ahead and update our result array. And then we now have 71 on the top, and that also resolves that. We can go ahead and try and resolve all the temperatures that we can in order. And at the very end, we'll eventually get 75, but we can't do anything. And now 72 will go on the stack itself, and these will have been taken off. And we still have a strictly decreasing thing. So anytime we do find a temperature that's warmer, we'll resolve as many things on the stack as possible. And then we'll add it to the stack when there's nothing left. And at the very end, we will have all of our possible answers. And we'll maybe still have some stuff on the stack, like maybe the 73 at the end doesn't get resolved. But in that case, it's fine. We have put a default of 0 into all of the spaces in the array, so we don't really have to worry about that. Exactly right. And this is something that's a little bit hard to see from the problem here, but if you think about like you're trying to resolve data with the most recent available data. So like you don't want something that's going to allow you to look at like the first thing you saw a long time ago. You want something that's going to show you just the most recent value so that you can resolve it with the most recent available temperature as well. We want our temperatures to be in proximity to each other, and so a stack here kind of makes logical sense. So let's go ahead and write this really quick. Res is equal to 0 times len temperatures. And now what we can do is we can do while I in temperatures should just be able to do this since it's iterable. And actually, I don't want to do this. Never mind. So what we want to do is we want to be able to get that index of what's currently in there as well as the temperature itself.
Use 4 if you're going to be doing it like that on a range.
You're right. And then temp is equal to temperatures of I. And so this, we now have our index and our actual thing here. So we can look, let's go ahead and create a stack here. Our stack we could do as a linked list, but in this case, that's a little bit overkill, and we're going to represent this just as a list instead. And so our stack is going to be a new list that is currently empty. Stack index equal to 0. Or let's try a -1. And let's make sure if stack index is not equal to -1 before we try and check if something's on the stack. And if that's true, and stack index is less than temp, then we can go ahead and resolve it. And the way that we're going to resolve it is we're going to take whatever that difference is between our current position and the index. We're going to stick into res. So that means that we have to store in our stack the actual index of the temperature that we want to resolve, not the temperature itself. We were drawing it out so it would store like 6973, but we need to store the index so we can go back and get that temperature. So actually, this should not even just be stack of stack index. This should be temperatures of this disgusting thing. Let's take this out here. Temp index. Old temp index. And if this is true, then we can set res of old temp index to be I minus old temp index. So if the case, in the case of where 72 resolves 69, that'll be index 0, 1, 2, 3, 4, 5 minus 4. All right, and if we take something off, then our stack index must be subtracted. And at the very end, when we have nothing left to resolve, so this should not be an if, this should be a while. And this is going to cause some issues here in a second. All right, we're going to fix this in a second. At the very end, we will go ahead and set our stack element, stack index plus equal to 1, stack index is equal to temp. No, our index. Okay, so what this is going to do that's going to cause an issue here is that our temperatures in our old temp index, that's what we want to get, but we have to update this afterwards. The danger here is that stack index could now be -1.
Another thing is also, if you're going to be adding onto the stack, you can't index into it because it's currently empty. At no point are you adding onto the stack. So if you want to add something onto the back, you can do .append, and that works.
Okay. We're going to stick with this for now, because I think that this is going to be fine. So if the stack index is not equal to -1, which means it's not empty, then we will go ahead and get our index with whatever's on the top. And if that temperature on the top can be resolved, then we'll go ahead and resolve it. Otherwise, we will break out. All right, so let's go ahead and try and run this. Let's index on range. Oh, we can't even get if it's -1.
You have to push it onto the stack with .append.
Can I not just stick it into the index?
No, no.
Okay.
Because the thing is, you initialize it to a size of 0.
All right. I didn't spell it. Lots of fun stuff here. All right, this one doesn't work either. What am I, like, do I not understand how for like a range loop works? This doesn't make any sense. So 73 gets resolved. 74. What am I not understanding here? 73, 74, 75, 71, 69. Okay, so it is iterating in the right order. So we get the temperature, check if our stack is not empty. If so, we get the index on the top of our stack. Let's try this. So why is this always coming back as 0? As if stack of stack index doesn't exist. All right, this is more debugging to be done another time. And this is why trying to give live presentations is never a good idea. All right, so this is the approach that we have here. Again, this is another example of why it's important to just do this in a language that you're comfortable with. And with that, I'm gonna go ahead and turn this off. I'm gonna pass control over to Zane to try and cover a couple of other problems before we end today.
Just give me 1 second, guys. Hey, can you give me permission to screen share?
Should have it. Apologies.
No, that's okay. Okay, can you guys see my screen? Yes, okay, cool. Okay, so the question, now we're gonna go on to the slide or the question for binary trees, binary search trees. So for everyone in CS1 or CS2, you guys are familiar with these, but if you aren't as familiar, then let me just explain it real quick. So binary trees are pretty much kind of how it sounds, binary in nature. So you can have at maximum 2 children to every node. So a node looks something like this, and you can have a left and a right to it. Sometimes you can either have something there or something not there. So in a case where there's something there and something not there would be something like this. So you can have one node right here. It can have a left. This left is currently null or none, well, whatever language you're in. Then this right child is an actual node, so it's non-null. So pretty much binary trees are a way to maybe represent data or store data, and they come up a lot in a lot of questions on Leetcode, or even in some interview you might do some technical interviews. So yeah, that's pretty much it for what binary trees are. Now there's binary search trees, and just real quick, binary trees, they typically hold some sort of information. So let's just say 3, 5, 6, etc. And when it comes to binary search trees, which is what the focus of this problem is it's pretty much a way to organize and efficiently search for values in a binary tree by organizing in a certain manner. So for those familiar with binary search, just a quick little explanation to that. Let's say you have a collection of values. So let's say we have 6, 12, 15, 20, and 26. And you want to be able to efficiently search for values without having to check every single value at a given point. Like let's say you want to search if 20 is in there. The way binary search works is it starts at a midpoint, and so you're going to have a left and then a right, and it has a midpoint. And based on where that value is, and by the way, this only works on a sorted sequence. So notice how these values are sorted based on where the midpoint lands relative to what you're searching for. So if we're searching for 20, we know that 20 falls on the right of the midpoint that we're currently at, which is 15. So we're going to move that midpoint past the previous point because we know that it was not at this location that we had 20. 20 comes after the value at this index. So now we're going to end up going to this side of the list. Effectively, we kind of cut it in half. So that's kind of the same idea that we're going to be using with the binary search tree. So we can, let's just say we organize it like this. So let me just erase this example. So say we have 15, then on the left of that, we're going to have 12. On the left of that, we have a 6. Let me just add some more values. Okay, and then 20, and 26, and let's do 18. Okay, so this is an example of a binary search tree. So notice how everything on the left of a node is lesser than it. So to the left of this 15, we have a 6, 12, and 14. So all those things are less than or equal to 15. Meanwhile, on the right of it, everything is greater. So we have 20, 18, and 26. So all these elements are greater than 15. If we were to kind of explore further down that line, at 20, everything to the left of 20 is lesser than it or equal, and then everything to the right is greater. So 26 is greater than 20, and the same thing applies throughout the whole tree. So 6 is less than 12, etc. So that's pretty much the whole idea behind a binary search tree. And you can easily, just like you did in this in the binary search algorithm, you can apply that on a binary search tree, because at any given point, you're gonna be cutting off, assuming or basing on how the tree was actually kind of structured, you're gonna be cutting off about half of the elements. So let's say we're searching for 18 again. We're gonna say, okay, at this midpoint of 15, where does 18 land on the left of 15, meaning lesser than or equal to, or is it greater? So we know it's going to be greater. So that means we go to the right, and at this point we're right here, and that effectively, just like in this example where we cut off this half to search for 20 on this side, we're going to effectively cut off half of the tree at this point, and we're not even going to consider it. And now at this point, we're going to make the same question. Is 18 less than 20 or equal to? Yes, it is. So we're going to go this way, and that effectively cuts another half off. So that's kind of the whole idea. They both end up cutting off about half of the search space or solution as you search for elements. So that's just a quick preface into how binary trees and then binary search trees more specifically work. So this problem is called k smallest element in a binary search tree. And let's just read it. So given the root of a binary search tree and an integer k, return the k smallest value, one index, of all the values of the tree. So let's just see this example. So we have this input, which represents this tree, and we have a k of 1. So just to translate this, for those that didn't understand, let's say you have these values in the tree. If you wanted to get the values in sorted order, the k smallest value would be if k is 1, the k smallest value would be 1, because 1 is the first smallest value. In this example, we have a bigger tree, and we have k equals 3. So the third smallest value in this tree is 3. So, and I just want to say these examples are terrible because k represents the actual value of the node as well. So you might get kind of tricked, like, oh, maybe you're looking for 3, or maybe you're looking for 1, but really it means the third smallest value, and this is the first smallest value. So if you were to get all these values out of here, and you were trying to, find the first smallest value, you would just want to stop whenever you actually hit that. So there's multiple ways to go about this. So let's just explore those different options. And we're going to touch up real quick on some things from CS1. So back to this example. For those that are in CS2, I'm sure you guys remember in order. So the whole process of in order is whenever you're at a given node, you actually recurse left, then you come back up to the node, then you do whatever you want to do at this point, and then you explore the right subtree. And then you kind of just repeat the same thing. Go left first, come back to this point, then you go right. So if you guys know that whenever you have a binary search tree and you want to get all the values in sorted order, what you do, you follow the in order traversal. So what the in order traversal will look like in this example would be the following. So we can start at 15. Like I mentioned, go left. Okay, now we're at 12. We go left. Now here we're going to go left again. There's nothing to go to. So we're come back up to 6. So let's say we're going to collect these values somewhere. So we come back to 6. Okay, 6 is the first smallest value. Then we can go to the right. There's nothing there. Now we come back up to 12. So now we're going to be at 12. 12 is the second smallest value. Now we can explore the right subtree. Now we're going to go left as per in order. We're going to come back up to 14 because there's nothing to the left. And now we have third smallest value, etc. So that's pretty much just kind of how it's going to work. So I'm just going to run through it real quick so you guys can see the process. I'm going to come back up to 15. So I'm just tracing out what in order traversal looks like. And this might help you guys actually evaluate how the problem or the actual strategy that we're going to use. So if we get all these values in sorted order, so I'm just going to skip a couple steps here. Once we actually end up running through it, now we have all these values in sorted order. And what we can do with this is now we can easily say, okay, what is the k smallest value? So let's say we're given a k of, let's say 4. So given that it's one index, meaning you guys know how arrays usually start at 0, 1, 2, 3, 4, 5, 6. The fourth smallest value, if we adjust it up, would actually be at index k minus 1. So let's say array of k minus 1. So k minus 1, if we're looking for the fourth value, we're going to have 4 minus 1, which is equal to 3. So at array of 3, we have a value of 15. So this is the fourth smallest value, and you can see that from, this is the fourth value in the list. So our answer would be 15. If we had 6, it would actually be, this does not look like a 5. Sorry. Okay. If we wanted to find if k was 6, we would actually be returning 20 because 1, 2, 3, 4, 5, 6. So that's kind of the idea of how we're going to solve this problem. So let's actually get into coding it. So we're just going to use this naive approach, and then there's another approach that I kind of want to expand into as we go. So let's start. So first things first, we're going to want to have somewhere to actually store these values as we go through the in order traversal. So let's just define a stack. Oh, and by the way, I just want to say this, guys. I know in Python, you're not supposed to use semicolons, but I use semicolons in Python. It's a weird quirk I have, but the reason is because whenever I go back to Java or I go back to C, then I forget, or C++, then I might forget to actually do these semicolons, and you guys know how annoying that is. So I just always do it. It doesn't affect anything. Your code will still run just as fine, but yeah, it's just a thing I have to do. If you don't do it, it's fine. But just so you guys know that's why that's there. That looks like I got a comment. Oh yeah. I mean, yeah, it's a good strategy, trust me. So let's create another function now that we have stack initialized. So we're going to want to recurse. So let's just call this function recurse. We're going to do recursion for this. It's easy. Then we're going to have a root node. And then we're also going to have this stack we're going to pass in. So let's just call it STK. Oh, and also in Python, since this is part of the class, we're going to have to do self. Okay, so the base case always is when you hit null, which in Python is none. So if root equals none, then you're going to want to return none. Actually, you're just going to want to return because we're actually not returning any values up. We're going to be storing everything into the stack. So whenever we hit these terminal points, we're done. Like we don't want to do anything with that. We don't want to return anything. And like I had mentioned, when you're doing the in order traversal, you're going to want to go to the left first. Then when you come back up, once you've processed everything due to the order of the binary search tree, everything on the left being lesser than or equal to, you're going to want to come back up, and then you're going to want to store the value at the current node you're at right now. And that'll produce it in sorted order. So let's do stack.append. And then we can just take the root value. So that's just going to give us the node where we're currently at. So if we're right here, it's going to give us 1. If we're right here, it's going to give us a 6. Then now we can recurse to the right side. And this will give us the actual in-order traverse. So let's just run that. So self.rec, let's pass in the root and let's pass in the stack. And then now we can just create the stack. And let's just see what happens. Okay, so this gives it to us in sorted order. Let's also just try out this other example. You can see that it gives it to us in sorted order. Okay, good. It gives this to us in sorted order. And now what we can do at this point, you can just return the stack of k minus 1. And this should work. Just for the same reason I had mentioned before, just do -1 and that'll give you the 4th in the 0 index list. So let's submit this. Yep, there we go. So that's the solution for this problem. Now I also wanted to introduce another solution where you actually aren't going to have to deal with the using a stack. So this, aside from the recursive calls themselves, they always take up like O of n calls, because you have to, you know, initialize the variables, the function itself, and all that sort of stuff. So it's going to be O of n space and time regardless. But if we didn't want to use a stack, there's another way to go about this. It's kind of weird, but trust me, it's kind of cool. So what I'm going to do is I'm going to leverage kind of a global variable in recursion, but by using an array. So let me just explain that. For those that know, you know, C and CS1, you guys have probably heard pass by reference or pass by like pointers pretty much. So whenever you have an array, it's somewhere stored in memory, right? And whenever you pass it into a function, let's say I have a value of 4. So let's say I put the value of k into a location in memory. Then if I decide to change this value as I'm going through the recursive calls, it will actually, it'll stay the same regardless of what recursive call we're in. So why might that be relevant? So if I change it to 3, and let's say I'm in this recursive call right here. If I change it to 3, when I'm here, assuming I do nothing, it'll still be 3. When I'm here, and let's say I haven't changed anything, it'll still be 3. Meanwhile, let's say we start at, let's say we're trying to target the value at index, let's say 3 right here. So we're going to start off here. So we're going to have k equals 3, and we're going to have this in an array. So we have 3 in an array. Since this is passed by reference, like I mentioned, as you change it through the calls, it'll stay whatever it used to be. So we're going to end up going here. We're going to end up still going left in the in-order traversal. Now we're going to be here, and we go left, then we come back up here. Now we can change this and decrement down to 2. And this is going to keep its state regardless of what recursive call we're in. So now we're going to go to the right. Okay, there's nothing there. Now we're back at this point. So it's kind of confusing. I'm tracing over stuff I previously wrote, but now we're going to be back at this point. Now here, we're going to check, okay, is this number at 0? It's not at 0 yet. So we're just going to decrement to 1. But notice, regardless of the recursive call we're in, it's still keeping its same value. That should change. Because normally what happens with recursive calls, you can pass things down. But let's say if I was passing down at this point, in the function, I was passing down k, and k was 3. If I decrement it in this call, when I come back up here, the value that I changed 3 to in this call is not going to transfer up here. It'll just come back to what it used to be. So 3. So it's not going to save the state. Meanwhile, if you use this tactic, then it would. So now let's go to the right. Now we're going to go to the left. Okay, now we're going to come back here. Now here we're going to decrement to 0, and this is going to be the k value, the k smallest value. So notice how we didn't have to use a stack and collect all these values as we went. We can just use and leverage the pass by reference, and then we can say, okay, now at this point, k equals 0, return this value, and then we're going to be good with this value. So let's just kind of demonstrate that. And just for this solution, I'm going to leverage something else that that came in the problem. So notice how we have the values are from 0 to 10 to the 4. So this is 10,000. So this is 10,000. So from 0 to 10,000 inclusive. So we can, like, and this is what I mentioned with leveraging the constraints, we can actually use values outside of this range to kind of say, okay, we didn't find a solution on this side. We didn't find a solution on this side. But whenever you find a value that is within this range, return from a recursive call, that is the solution. So for example, in the case that we have so let's say, just give another example. In the case we're looking for the second biggest value, so let's say 26, 10, and then 53, we can end up going down this way. Then we end up going down this way. We found nothing, right? So we're going to end up returning -1 because -1 is outside of this range, right? So if we return a -1, this is going to signify we didn't find anything on the left side of this node. Then now we come back here and we're looking for k equals 2 again. So now we can end up decrementing this. Then now we go to the right. We didn't find anything. So we have -1, -1. And now we can compare, okay, did we get a value that is not -1? Or like pretty much did we get a positive value? No, we didn't. Okay. And also this was not a value of K was not 0 at this point. So we're just going to keep going. We're going to return a -1. So this side is going to return a -1. Now at this point, we're going to decrement, we're right here, we're going to decrement K. So we're going to be at 0. And at this point is where we're going to say, okay, this is where the K value is. So we start at 2. So this is where it's going to be at. So now we can just return this value. So we're going to return 26. And this is going to be the solution for this question. And we could have kind of ended up going a little bit further with this. So let me just signify the point, because this is kind of like the root node. So it's not as nice of an example. So let's say we go down to 1. So we're going to end up going here, go to the left, nothing. Come back up here. Now it's going to be 0. And we're going to return up this value. So we're going to return 53, right? And now from this left side, remember on this left side, we had a -1. And then on this right side, we have a 53. Since values can only be in this range, whenever we find something that's not out of this range, this is going to be the answer. So now we're going to end up just returning 53. And that's going to be the solution. So I hope you guys understood that. It's kind of a different way of thinking about it, but by leveraging the constraints, you can kind of validate yourself as you're going through the tree. So let's also code that up real quick before we get past on time. So let's just go here. So we're going to have a counter, and we're just going to pass it in with an array of k. Then now we're going to call, so we're going to return self.rect of roots, and then the counter. There we go. So like I had mentioned, if we don't find anything, so it's none because we return -1, then we're going to have a left recursive call. Right, and then when we come back up is when we're going to want to decrement the counter. So counter of 0 minus equals 1. And now at this point, if this counter value is 0, so counter of 0 equals 0, then that means that this is the location of the value. So return the root.val. Otherwise, we're going to want to go right equals self.rect root.right. And if you think about it, if we didn't find it on the left, or actually, let me just do this right here. So if left does not equal -1, then you're just going to return left. So if it's not -1, that means we found it on that side. Then and then we decrement the counter. If we found it at the current node after we've searched our left side, the smaller side, then we just return that value. Otherwise, if it's not on the left and it's not where we are right now, it can only be on the right. So at this point, we would just return whatever comes up from the right, because we're pretty much going to assume that the answer is in there, because they're not really telling us for a case where k is out of bounds. It's always going to be within the bounds of how many nodes there are. So there's always a solution. So if it's not on the left and it's not where we are right now, it has to be on the right. There's no other way. So let's just check if this answer works. The solution works. Yep, there we go. So you see how much faster it was. It's kind of arbitrary. Like sometimes, let's just try it again. Okay, you see it. Okay, well, never mind. Well, yeah, it's a lot faster because you're not, doing a lot of appending and all that sort of stuff. So, yeah, that's this question. So if anyone has any questions, let me know real quick before we move on. Okay, so now let's go on to the next question for next session. So we have tries. Now this question is going to be a little more complicated than the other ones, but let's just go to it real quick. Oh boy, let me just delete that real quick. There we go. Okay, so we have this question: design and add search words data structure. And design a data structure that supports adding new words and finding a string if a string matches any previously added word. So implement the word dictionary class. It initializes the object. Then we have an add word function, which adds a given word into the data structure and it can be matched later. We also have a search function that returns true if there's a string in the data structure that matches the word or false otherwise. And the word may contain dots where the dots signify can be matched with any letter. So what does that mean? Let's just look at these test cases. So we're going to add in bad, then we're going to add in dad, then mad. So we're going to want to search for pad. Pad does not show up because we only have bad, dad, and mad. Then we want to search for bad. So bad is definitely in there. Then we have dot AD. So remember, dot pretty much means you can go for any letter at that current point. So we can opt for B or D or M, and then we still have something that ends with an AD, a fixed AD at that point. So in that case, there does exist somewhere that ends with AD or with this like template. Then here, we want to search if there's a word that starts with a B and then ends with any two letters. So we have one word that starts with a B, so we have bad, and any letter at this point can be A. And then for the next letter, we can have any letter, which is D. D counts as any letter. So then we can say, okay, we can find a solution for that. So some interesting constraints. The word length is going to be from 1 to 25. It's all going to be lowercase. And yeah, that's pretty much it. Oh, aside from the dots. There's going to be at most 3 dots. And that's kind of important because if you have like maybe, I don't know, like 20 dots you can go through, that can take forever. So that's kind of like a good thing to constrain. So let's think about it. If we have a word dictionary, what does that sound like? That sounds like, for those in CS1, CS2, that sounds like a try. So pretty much what a try is, it's a word, it's a way to store and search for normally strings. So let's say we wanted to add bad, then dad, and mad. Just use these examples. And also let's have Leetcode. That's kind of long, but so we're going to want, so every try node is going to have an array or some sort of collection of values representative of, like, the next levels you can go to. So in this array, and also we also have a flag variable. So as of right here, we can say, okay, we have a B. So we're going to want to add bad. So we're going to add in the first letter B because we don't have a B at this point. Then we're going to want to add another. So F, and now we're going to want to add an A because we don't have an A. And now at this point, we're going to want to add a D. And here is really this node signifies the end of the word bad. And since we want to insert it, then we can just stop right here, right? So we can just stop right here and turn this flag on to true. So true. So this represents the actual word. Then, it's going to be the same thing with all these other ones. So we're going to use a D instead. And I'm not going to draw these things out again, but let's just do false. Then we can have an A, then we can have a D again, and then this is going to be true. And yeah, you guys can kind of get the idea, but I'll draw it out. Now, Leetcode, that one's going to be a lot longer one. I should have chosen something smaller, but yeah, let's just say Leetcode eventually. A and then D, so this is going to be false, false, and then at the end we're going to have true. Okay, so this is kind of the structure of a try, and specifically where I want to use a try in this question is because we're going to want to efficiently search for strings, and kind of what the solution for a case where you have like you're trying to search for something with a dot would look like. Let's say we had two different ways we can go from this point. So let's say we want to add a Z, right? So I know A comes before C, but let's just add a Z here for space reasons. And let's just say BZ is a word, so just true, and yeah, that's pretty much it. So now let's say we had a term that we're searching for, B dot, and then that's about it. Or actually, let's do this, B dot D. So now we're going to search, okay, from here we have a B. So let's go down to this level. Now we're going to look at this point. So we start off here. Now we're going to look at this point. Now here, let's go to, remember, this can be any letter at this point whenever you have a dot. So now let's just go to every possible place we can from this node. So in other words, let's check all of our children that we can go down. So what that means is we're going to, let's just explore the lowest one first. So yeah, I know A comes first. Let's do this one. So let's go through this subtree. So now we're going to explore this one. Then now we're going to check in here. We ended up taking the dot at this point. So we ended up moving down towards any letter. And now we're going to be right here. We're going to say, okay, for at A, do we have a D under us? Yes, we do. So now let's go down that way. And now at this point, we're past the word. So now we've signified, okay, we've gone the full length of the word because now we've passed it. We've verified. The only way we can get to this point is if everything before us was good and in check. So now at this point, we're done. So at index 0, 1, 2, whenever you hit the length of the actual word, that means you're done. And we're going to want to return what the state of that word is at that current point. So this can be true. This can be false. So here we have a true. So in this case, we're going to want to return true up to this recursive call. So we have a true. Then we're going to want to return this up, true. And now we can, if we want to, we can explore down the other paths. Remember, the point of this problem is to search for any word that follows the schematic. So whenever we find one, we're pretty much done. We don't have to keep searching other parts of it, but to signify and kind of show how it's supposed to work, then we can end up exploring here after we've gone here. At this point, we're going to be right here. I want to see, okay, does Z have a D under it? No, it doesn't have anything. So just return false. So this is going to return false up here. And now let's just check all our options. So we have a false, we have a true. Did we find it here? Yes, we did. So now let's just return true up here. Okay, and then now at this point, we've already searched down B. In the case that we had a dot here, we would have searched down all these paths, so that's just kind of like how it works, what the whole idea behind it is. So first things first, let's code up the insertion, because insertion is kind of the key of it. We kind of have to do that first. So let's just initialize what the try is going to look like. And I'm just going to say this, the way I code up tries is a little weird for those that know Python. So I'm going to use a hash map, but you can just think of it as a collection of values. So this is really my node. And you can think of it as kind of like a pointer to a node, since this is like a list. So this is telling us if this word is, or if this node is a word, and this is kind of like that array of children that I was mentioning. So I'm going to use a hash map just because it's kind of quicker to code up doing it this way. And I'm not using a class, so yeah, I hope you guys can follow along. If you have any questions, let me know, because this implementation is a little kind of weird seeing it for the first time, but trust me, it works out well. And it's actually a really nice way to code them up. So, okay, if we're going to add a word, we're going to want to start at the very root. So let's just call it current node equals self.root. So now we're at the root node. And now we're just going to want to iterate down the path of the current word that we're inserting. So for letter in word. So for every letter in the word, what we're going to want to do in the case of this example right here, let's say we're adding in bad, right? So it's bad. It'll be right here. We're going to check in this list or in this hash map. Okay, do I have a B? No, I don't have a B. If I don't have a B, then add that B in and attribute to that B a node. So in terms of a hash map, it would look kind of like the key. So this is our key. We're going to add in a B. And then now we're going to add in another node, which kind of looks the same. And we're going to have true or false. Then once we're in here, we're going to say, okay, does this node have an A, right? It doesn't. Okay, so now we're going to do the same thing. We're going to create another node in here, or sorry, a key, and then that's going to have its own node. And that's kind of like the structure of it. So I'm kind of creating the try nodes as I go. So yeah, that's kind of like the whole idea behind it. Typically in C, what you would do, you would just use an array, but yeah, I just kind of like this. It's the same idea, but I like this implementation more. So if at the current node, so let's just destructure it out. So I'm going to take out this hash map. So this is like the children, and then this is the actual state if it's a word or not. So let's just say children, and then is word node. I'm going to take that out from the current node. Okay, so if the current letter is not in the children of node, so that means like an example I gave, if at the current node we don't have a B under us, then add it in. So we're going to do children of node letter equals, and then we're just going to set it equal to another node. So we just create a new node. And now we actually have to just go to that node. So we can just set the current node equal to children of node of the letter. So this is just going to take us to this reference of this list that we just made. And if it was already in there, we would just go to either way. So that's fine. And at the very end, after you've done all this, your current node will be sitting at the terminal node. So for example, if we added in bad, we're going to be sitting at the very end of this iteration. We're going to be sitting at the node representing the D in bad. So since we're going to be at that last node, we can just do current node of 1. Remember, index 1 is the state of whether or not it's a word or not. So since we're adding it in this function, we're just going to set that into true. And that's going to, so what we've done right now, we've just added in the word, and then now we just marked it as a word in the try. Okay, so that's pretty much the add word function. So let's just go on to the next one. So back to the searching part where we're going to want to search like, the different possible solutions. We're going to want to do this recursively. So I'm going to make up a different function. So I'm just call this direct search. And we're going to want to have the word we're going to be searching for, or like let's just say schematic or whatever. Like, no, template. Template's a nice word. Okay, template. Then we're going to want the actual index. And the last thing is we're going to want to have the actual node we're at. So node. Let's just call it root. Actually, that might be confusing with this up here. So let's just do node. So again, okay, so our base case is really going to be whenever we hit the very end, right? So whenever we hit the point where index equals the length of the template. So this is like the term you're looking for, like this right here, b dot dot. Then at that point, we're going to want to return whether or not the current node is a word. So remember, each node has its like children and then its word status. So let's just say node children and then node word or node is word equals, and then I'm just going to set that equal to the node. And now we're just going to want to return whether or not it's a word. So now we've gone as far as we can. The only way to get to this point is everything before us was valid. So now we have to return what state we're up. It could be a word. It could not be. It might not be a word. But we just have to stop at this point. Then the other cases that we might run into is, okay, let's say we have a regular letter. So let's say we have an A and we don't have a dot. That means we can only go down one path at this point. So we have to take A in this case. So let's just handle that case. So if at the current index we have, or we don't have a dot, meaning we have to go one specific way, one specific letter, then what we can do is check if in our children we have that given letter that we're currently at. So let's also do this current letter equals template of index, so it's less confusing. Current letter, right? And then now if the current letter is not one of these special cases, then we also have to check if current letter is in, or if current letter in node children. So is it a child of the current node that we have? If so, then let's go down that way. So self.rec search of node children of current letter. So now let's go down to that further node if we have it. And then we're going to want to keep the template the same. And now we've just moved an index, so index plus 1. Now, otherwise, if we are at a dot, this is the case where we're going to want to search all possible ways we can go, right? So what we're going to want to do is we're going to want to iterate over all possible children we might have. And in Python, since we're dealing with hash maps, we're going to want to use a different style of for loop where pretty much we can like dissect the key and the value in the hash map. Because remember, in a hash map, there is a key that you're searching for, and then you have a value that you store to that key. That's the key is associated with the value, or the value is at the key, pretty much. So now we're going to want to iterate over every key letter and then key node in the node children. And you're going to have to convert that to items. So items just gives you an array. And then this just says, okay, give me the first item in that, like at each index or at each value, give me the letter and then give me the node. It's the same kind of thing as this. We're kind of unstructuring this out to two variables. It's the same idea. So now at this point, we're going to want to go down every path that we can. So let's just store answer. So answer of recursion. Because remember, this is returning true and false over time, right? So we're going to want to store that somewhere. And this part is kind of important in optimizing this solution. And you guys will see why. So let's do rec search of key node. So now this is going to be the node we're going to go to, then the template, and then index plus 1. So now we're moving a level further. So now let me just skip one step. In the case that we do all of these things and we don't find anything, we're just going to return false. That means at the current node, we didn't find anything. So we can just return false. Now, right here, I'm going to do something that might not make sense initially, but trust me, it will make a lot of sense. And you'll see why it optimizes. So whenever we find a solution that we want, we're trying to search if something is there. In the case that it is there, we're going to want to kind of cut ourselves short and stop searching completely, because we don't want to search if we already know that we have an answer, right? So once you've found the first answer, you're going to want to stop immediately. You don't want to keep proceeding and searching, because if not, then you're going to do a lot of unnecessary searching. So if the answer of the recursion is true, then you're going to want to just return true. And this is going to cut you off a lot. And you guys are going to see why. I'm going to go back to the example that I drew out. But let me just, this code should be good. So let's just review. We check if the index is at the end, meaning we've hit the furthest point we can. If we don't have a dot, just go down the single path of that letter. Otherwise, then we're going to want to go to every letter, go to that node, and yeah, if we have a true solution, then return that, otherwise false. Okay, so this should work. Just to return self.rect search of the, so the node at the start is going to be the root node, then we're going to have the word, and then we're going to have the index, which is always going to start at 0. So let's see. Okay, so it's accepted, and I'm just going to mention this on this question. The runtimes are disgusting. Like some of these questions, like whenever you submit specifically this question, sometimes it doesn't work, sometimes it does with the same solution, even if you optimize. So I think, yeah, so look at this. Time limit exceeded on the same solution, like 14,000 or 17,000 milliseconds. So, you know, it can vary wildly. So sometimes your solution is right. It's just Leetcode, just takes slower amount of time to, you know, run the code. But okay, let's just run it and see what happens. This is going to take a while probably, but. And then I'll explain why this optimization is so important. It's only 2 lines, but, oh, okay, that was actually not that bad. But let me explain why that is. So back at this example, so we were searching for this template, right? So we had B dot and then D. Once we found this term right here, so once we found that this was true, and then we returned true up here. So we, at this point, this is where we did our base case. So this is where we did this check right here. We did this check right here. Okay, the index is now right past this point. So we've gone through the furthest one we can, return whatever's at that node. So we return true up here. And now, since we found the solution, we don't want to keep exploring anywhere else. We don't want to keep exploring anywhere else. So the reason why this is such a big optimization, let's say I ended up choosing something like a dot here instead, right? Let's say we had a dot here instead. And let's say we also had a bunch of other nodes, right? And all these other nodes can have a bunch of others, you know, extensions and all that sort of thing, right? You know, let's just do a triangle or huge subtree, right? So what is the point? Let's say I find a solution from here. So this is really the end of it. And then this is also going to be, and then we end up returning true from finding a solution up down here. What is the point of me searching all of this right here? If, or really up until here, since we're only going one level further, but what's the point of me searching all of that if I found an answer right here? We're just trying to search if something with this like kind of format appears. So the first one, we're done. So think about it. In this call, if we say, okay, we just got from this recursive call, in this code right here, we did right here. So we save the recursive call, and we're pretty much saying, okay, if this recursive call returned true, then return true up to the next call. So right here, we're going to say, okay, this recursive call, we just came up, it returned true. Okay, so now return true back up here. We don't have to keep searching. So we can just eliminate going down this way. Then now at this point, we just came up from A and we had true. Okay, so we found true. Then just, we don't have to search anything else. We can eliminate going down this way because we found an answer. And then now we can just return up here. And since we only went to one path, then since this was one specific node we have to go down, we don't have to go further. But let's just imagine we had a dot here, right? Then that eliminates us from having to search all of this, right? Because now we're going to be like, okay, at B, we just got an answer from this side. So then just cut all this stuff off, right? So that's the whole idea of that small optimization, because we're saying, okay, we found something, let's stop. We found something, let's stop. We found something, let's stop. Until ultimately you just return out of the function and you just return true. In the case that you don't find the word, you're going to have to search everything. And then, that's just kind of what you have to do. But in the case that you do find it, the first time you do, you stop, because it can really optimize things. I'm pretty sure if I don't add this, then let's just say I did this. So answer equals false. Then let's just store it, right? So we're just going to do answer equals true. And then we're just going to return it at the very end, right? So after we've explored everything, because we're doing recursion for every call, then let's just see what happens. So it still works. Now let's see if it runs like as fast. It probably won't. It'll probably time limit exceed. Maybe it might run. But yeah, look at that. Oh shoot, actually, well, but trust me, this is a big optimization. Just sometimes, like I mentioned, notice here was like 2,000 milliseconds. This actually wasn't as bad as other ones, but yeah, just trust me, that's a very important optimization to make. But that definitely aided me in getting to 7,000 instead of 9,000. The really important thing is it's fast enough to pass. Don't try to beat yourself on 7,000 milliseconds. I want to hit 3,000, because the whole point is if you can solve it, that's the key thing. So yeah, just don't beat yourself up over that. All right, so now we can go on to the next question. And by the way, the code for this is going to be provided at the very end of the slides when we release them. So we have the GitHub and we have our solutions there. So now let's go on to the next topic. So we have graphs. So those in CS1, this is not going to be a crazy graph. You guys have seen this. But those in CS2, this might be a little easy for you guys, but it's still good exercise. So we have max area of an island. So this is another problem. So let's go to it. Okay, man. Sometimes my code is really bad, guys. Just ignore what was there. That looked disgusting. So now we have max area of an island. So you are given an m times n binary matrix, and an island is a group of ones representing lands connected four directionally, horizontal and or vertically. You may assume all four edges of the grid are surrounded by water. The area of an island is the number of cells with a value of 1 in the island. Okay, so return the maximum area of an island in grid. If there's no island, return 0. So let's see what they kind of mean. So we have here an island of size 1. Right here we have an island of size 4. Here one of size 5. So we have, store this, we have 1, 4, 5, right? Then we have another one of 4, another one, and this is not any particular order I'm going in, just kind of listing them out. Then here we have 6, and then here we have 5. So the maximum island is going to be the maximum size across all of these values, which will give you 6. So how do we actually end up doing it? Does anyone have any suggestions as to maybe what algorithm we might use? I'm hoping someone can say, because this is CS1 stuff. Professors may or may not have covered it, but I hope they did. But yeah, just give it another maybe 5 seconds, 5-10 seconds. Any suggestions? Okay, so flood fill is an algorithm that comes to mind with this. So you guys have probably done flood fill, and pretty much what it does, it just kind of, just like this says right here, 4 directionally goes in, up, down, left, right, and in some cases you might want it to go, in more directions than that, different directions. But the classical way is you go up, down, left, right, and you explore all area or all locations in the grid that follow a certain criteria. So in this case, we want to see the biggest island, and we know that the islands are represented by a value of 1. So this is land in an island. So if we see a 1, we know that, okay, this might be the whole island, or it could be part of a bigger island. So for example, in this case, it's just the first one that we see is just, 1 block for the island. Then here we see a 1, but then this is actually a part of a bigger island that it's connected to. So the way flood fill kind of works, let me illustrate, is, so let's say we have same kind of thing. So we have 1, 1, 1. Okay, this should be good enough. So again, we move in all directions, right? And we're going to want to go through the board as we normally do. So from the first row all the way up to the end, the last column of the first row, and then the second row from the first column to the last column, etc. But whenever we hit the first one, we know, okay, this, like I had mentioned, this is either an island or part of an island. So we can start to explore, right? So we can search in all directions. And let me just draw a box around this so we know where the ends and the edges are. So if we're right here, we're going to want to look all around us. Okay, can we go here? No, this is out of bounds. This is, remember they mentioned the edges of the board are technically going to be water. So really, this just means we can't go there, or we don't have to go there because we're not looking for water. We're looking for islands, and islands are represented by 1. So we are not going to go here. It's also out of bounds, so we can't index there. And let's say we want to go down here. Okay, we can go down this way, right? And we can go the same style of things that we did. So we went up, left, down, right. So let's just follow that order, right? So we're gonna go like this. We're gonna end right here. So now we're at this point, right? But we're gonna go up. So the problem with going up right now is that you're gonna be like, oh wow, there's a 1. So let's go to the 1. And since this is a 1, you're gonna go up again, you're gonna go left, and you're gonna go down, and you're gonna say, oh, we have another 1. And now you're gonna be back here, and since the order you're going in is up first, and really it doesn't matter the order. If you don't do one step, this is always gonna happen. So now you're gonna say, okay, now there's a 1 above me, let me go back. Up, left, and you're gonna go back, so you're gonna keep going back and forth infinitely. And this is one of those things that hurts you when you're doing certain types of recursion, really most types of recursion, where you might go over the same place twice. You're gonna want to have a way to know, okay, I've been there and I don't want to consider it at all anymore. So when we first get to this point where we see, okay, this is an island, what we're gonna want to do before we end up moving anywhere, we're gonna want to just mark this as a 0. So this is gonna say, okay, now we can go up, we can go left, or we can't go, sorry, we can't go. Then now we're gonna go and look down. Okay, we can go this way, let's go this way. Now here, we're gonna mark this as a 0. So now we know we can't go there. But the cool thing is, remember the order we're going in. Let's check up. Oh, we can't go up because it's a 0 now. The algorithm doesn't necessarily know if that was where you came from based on how we're gonna code it, but we're gonna know, okay, we can't consider that because it's a 0. So either there's only water there, there's only ever been water there, or maybe it was changed before. But as of right now where we are, we know that we can't go there at all. And that's important because that's going to make us not go, infinitely back and forth, right? So we're going to check here. Oh, we can't go there. So we're just not going to consider it. So we tried going up, we can't go. Then now let's go left. We can't go, it's out of bounds. We can't go down, it's a 0. So stop. We can't go right either. So we just stop. So we know that the amount of elements we could reach from this point, we can only reach itself, right? We only got here, so we're just going to return a value of 1, right? So this is a size of 1. Let me do this in a different color. Let's do orange. Okay. So we return 1 from here. Now at this point, we have gone up, we've gone left, we've gone down. Now let's just explore the last direction, which is to the right. So now we're gonna go this way. And okay. So we're gonna go here, we're gonna mark it as 0. And then we're going to go in the same directions that we always have. So we're gonna go down, up. Oh, and by the way, we're storing kind of like the land values as we go. So what that means is every island has a 1 initially. And whenever we come and we explore another island, we're just going to increment. So this is, we initially started with 1 because this value is a size of 1, like this island. This is 1 piece of land right here. And we ended up coming from here. We only found 1 piece of land. So we're just going to add them together. So now we're going to know that at this point, we found 2 so far, right? Now, yes, so back to where we're here. We go up, we can't go there. We can't go back because this is a 0, so that's why it's important, again. No, we can't go that way. We can't go down either, but we can go to the right. So let's go to the right. And yeah, this has a 1 again. Now, going to be here. Turn this into a 0. Again, this stores a 1. Then now we're just going to check the 4 directions in order. So can't go here, can't go back here because this is a 0. But we can go down, and we end up going down. Now from here, we're going to same order. So check up, can't go up, can't go left, can't go right, or down, and then we can't go right. Again, this stores a value of 1 because this is the size of this location. So we got a 0 from here. We didn't get anything from here. We didn't get anything from here. We didn't get anything from here. But we do have itself. So this was a point of land. So now we can just return 1. So this returns 1 up here, right? And we can do 1 plus 1 is going to give us 2, right? Now from here, we have to search to the right. So to the right, there's nothing. So now we're done. So we have a value of 2 at this point. Now we can return this to the call that called this one. So that's going to give us 1 plus 2, which is 3. And if you notice, we know that from this point, including this point, we've gone like this, right? In total, we've gone to 3 values. So now you can see how returning up the recursive calls is representing what we've explored, including ourselves. So this is 1 land node. It used to be a land node. This is 1 land node. This is 1 land node. So now we have a total of 3 from this point. Now, from here, we're going to return 3 because we've gone left, up, down, right. Return 3. And remember, when we had gone from here, we had to return 1. This already was a size of 1. So we have a 2 here. But then we add 3. So now we end up having 5. So now we know everything from this point on, because we've gone left, up, down, and right, everything from this point on at this location, we found a total number of, or we found a total of 5 pieces of land, which represents the size of the island. So now we're done. We've searched everything. And now we don't want to consider anything else because, you know, we've gone in all directions. We've marked everything 0. So we're not going to consider again. So now we have a size of 5 for this whole island right here. And I apologize if this is messy. So this whole island right here in red, we know it's a size 1. And also all these values are 0, right? So all these values are 0 right here, right? So we've only searched this point in terms of iterating through the entire matrix. So remember, we were searching through the matrix. Now we're going to end up going to this point, and we're going to see, okay, this has a 0. There's probably not an island there. This has a 0. There's no island here. This has a 0. There's no island here. Same thing here. It's still a 0, 0, 0, 0. Another 0. But then we see a 1. Okay, so there's probably an island here, or there is an island there. So now we're going to start the same process that I had done for the other one. So we're going to be right here. And we're going to do the same exact thing. We're going to, oh yeah, mark it 0. This has a size of 1. Then we're just going to search above us. Okay, 0, we get nothing. And another 0, we get nothing. Another 1, another 1. So 0 plus 0 plus 0 plus 0 plus 1 will give us 1. And this island, we only found 1 value, right? So this is 1. And then this whole thing was 5. So what is the maximum between those two? We have an island of size 5, size 1. We take the max, and our answer is 5. So this is kind of the framework of how we're going to solve this problem. So I just explained flood fill visually. Now let's actually code it. Remember, we have to go in 4 directions: up, down, left, right. And then we're going to want to mark where we are so we don't go back there after we move away from where we are right now. We also going to want to just keep a counter that we add to. So just like we added 1 to this one, 3 to this 2, etc. And yeah, just take the maximum after every island we search to. So let's just do that. Okay, so first things first, let's iterate. So let's just take the dimensions real quick. Because the code can get messy if I don't do this up front. So they're just going to give us the number of rows and the number of columns. So now let's just iterate. Oh yeah, I use X and Y in my for loops. Just trust me, it's faster to code than INJ. So I did just like to use that. And now where we currently are. So if we have a piece of land, so grid of XY equals 1, then that's where we're going to want to start our searching. So our recursive call with flood fill. And remember, we're going to have, let's just call this self dot flood fill. And what are some things we're going to want to pass in? We're going to pass in the grid. Actually, we're going to pass in the X or Y. And we're also going to pass in the grid. And another thing we're going to want to pass in is just the dimensions as well, just to make it easier. We can get it from the grid in here, but if we don't have to, let's not have to do this part again. So we're going to call flood fill, but remember, this is going to return the island size. Now, so I haven't coded the actual flood fill yet, but let's just think about it. Once we get the size of an island, we're going to want to compare it against some sort of maximum island size. And since we're trying to maximize it, let's start at 0, because notice how if there is no island, return 0. So the maximum or the minimum size of an island is 0, because that just means there's no island, right? So we're going to want to maximize it based on what we find. And we know that if we ever hit this condition, it's always going to be greater than 0, because at minimum, it's just going to be 1. So maximum island size equals the maximum of whatever we currently have as our maximum and the island size. So let's just add this current island size. Current island size, right? And at the very end, we're just going to want to return the maximum island size. Okay, so now we actually have to code the algorithm, because I haven't really done anything with the flood fill. So we're going to have a flood fill function, and let's just set it up based on what we pass in. So X is our current location for the row, and then the Y is the current location for the column. I'm going to pass in the grid and the dimensions. And just one thing real quick. Remember in these examples, there are cases where we can go out of bounds, right? So for those that don't remember flood fill or do remember, we need an inbounds function. So we're going to have to just validate whenever we're going to go to a location. So if we're right here, we have to know, is going here going to take us out of bounds, or is going here going to take us out of bounds, or is going down or right going to take us out of bounds? So if we're right here, so let's say this is a 1 and we're right here, we want to check these positions. We know they're not going to be in bounds, but we're just going to have a function that verifies that before we go somewhere. Because if not, then, you know, since we're familiar with C more at UCF, you're going to segfault, or in this case, you're just going to get an error on Python. So we don't want that. So we're going to have a function that checks if we're inbounds. So just some restrictions on checking if you're inbound. At minimum, remember, arrays start counting at 0. So you're going to want a row index to at least be 0. You're going to also want your column index to at least be 0. You're also going to want to be less than n. So here we have a 5x5 or a 4x4 grid. So let's say we have a let's say we have something else. Let's say we have, give me 1 second. Okay, there we go. So let's say we have a 4x6 matrix. So this is our n, this is our m. So this is rows, this is columns. So we're going to want our values to be less than or equal to 0 for the row. We're going to want it to be less than 4, because remember in programming, for the most part, 0, 1, 2, 3, we start counting at 0. And in this case, we're going to want to be less than or equal to 0 and less than 6. So we're going to want to be from 0 to 5 inclusive. Okay, so that's just 6 exclusive. So we're going to want to check if we're following these conditions. So that's the whole point of the inbounds function. It's just so you know we're not on these edges outside. So let's do that. We have def inbounds. I'm going to pass in an x and a y, an n and an m. So the bounds. So return if the row index is good, or check if it's greater than or equal to 0. Same thing with the column index. And you're going to want to check if x is less than the end of the amount of rows, and if y is less than the number of columns. Okay, so now we're going to want to do the actual flood flow. So first things first, we're going to want to store a variable that represents the size. That size from this point. I'm just going to make it a long name so it's clear. So remember, this is kind of how I worded it. Size from this point on. Let's just say island size from this point on. Don't do this in an interview. This is kind of too much. Just call it size, but just so you guys just to clarify. Then remember, we're going to want to mark where we are 0 so we don't go back and forth, back and forth, back and forth. So we're going to want to say the grid of x and y equals 0. By the way, I appreciate everyone who stayed overtime. Yeah, I appreciate it. But we're almost done. We're going to wrap up soon. So let me just add some more space. Okay. So this again prevents, this is really the safety. So this prevents infinite recursion back and forth for, there you go. Just unlimited. Then now we're going to want the directions, right? So I actually forgot to do that. So we're going to want to create some directions. We're going to want to know how to go up, down, left, and right. So let's just do that in here. Directions. So let's just create a list of directions. So don't mind these parentheses. There's these things in Python called tuples. They're pretty much like lists. Yeah, let's just keep it at that. So they're pretty much like lists. So we're gonna want to go. So remember, this is gonna represent our x. This is gonna represent our y. So one of the directions we can take is if we decrement the x. So remember, x in programming or like in a 2D array, when you're going downwards, that pretty much means that you're going up. So let's just start off at +1. And we're going to want to go 0. So this is going to signify actually technically going up, but the way we're looking at it now, the orientation, we're going to go from here downwards. So let's just say this is down. Then we're going to want to also go up. So we're just going to go in the opposite direction. So it's going to take us from here up to here. Then we're going to also want to go left, right? So this is going to take our y and take us to the left right here to this area. And we're going to want to do the opposite. So we're going to want to go towards the right. So if we're right here, now we're going to go here. Right? So these are our directions. So for each direction, notice how there's 2 values. I'm going to do the same like destructure trick thing where you can just pull out these values and not have to index into them and all that stuff. And yeah, I'm about to use dx dy. Yeah, so I don't want to remind you guys of calc, but so I just kind of try to call it this, just so you know, it's like a direction or like a difference on the X we're going to apply. That's kind of like why I use this variable name. And the difference we're going to apply on the Y point. So we're either going to go from where we currently are, up, down, left, right. So for every location in directions, we're going to want to store the next X and the next Y. So that's the next X after we apply the change. So let me just make this more simple. So let's just do, we're going to take where we currently are, X plus the direction change on the X axis. Then the next Y is going to be Y plus the direction change on the Y axis. Now, okay, now we have the location of where we're going to go to now, but we don't know if that location, where we are right now, the only way we can be where we are is if it's valid, meaning it's inbounds. But we don't know if where we're going to go after this change is going to be valid, which is why we created the inbounds function, right? So there's only two criteria we don't want to go to. We don't want to go to a 0 because we're looking for islands, which are values of 1, not 0. And we also don't want to go out of bounds because then again, you know, computer's going to break. So we don't want that to happen. So we're going to do if self.inbounds next X and then next Y and then the N and the M. So if these values are follow these conditions of the inbounds, then and remember. So now remember the order of this is going to kind of matter. Since we're checking if these indexes are good, we can't just be indexing in up front because then how are we going to know if this like this might give us an error because you know we might index into something that's out of bounds, but we can check for that up front if we order this differently. So if we check if it's inbound and then we index into it after we know it's good. Because remember how these if statement works. If and only if this is true and we have an and, then we're going to go on to the next statement to verify. So this process is first, and this is kind of a protection against going out of bounds here. Equals 1. So if where we're considering going is land, then we're just going to want to go there. So let's just say further island size from next point equals self dot. Then we're gonna do flood fill. So now we're gonna flood that way. So next X, next Y, grid and M. So whatever we get from where we're going, we're gonna want to add that on to where we currently are. So this right here. So we take the island size at this point, it's going to start off as 1, of course. But as you go all the different directions, it can get bigger and bigger. So plus equals further island size from next point. Yeah, don't do this in an interview. These variables are too long. Okay, and then now at the very end is where we're just going to want to return island size from this point on. And that's going to kind of aggregate in the same way that I had mentioned here, where we had a 1, then we had a 2, then we had a 3. Then from here we had return a 1. So 1 plus 1 gave us 2. And then from here we got the rest, which is 3. So 5. So that's kind of the whole step there. And now that we have the flood fill, this should work. So just to recap, get the dimensions. Start maximum at 0 because that's the minimum case. We just don't have an island. Iterate through the matrix. If we find one piece of land, then we can search further to find others. And we can compare whatever island we find after we're done exploring with the maximum we have so far. So it's going to start at 0. In this case, then we're going to go to 1. Then we're going to compare these. It's going to be 0 versus 1. Then it's going to be 1 at maximum. Maximum of 1 and 4. Then we're going to have 4. Then here, maximum of 4 and 4, 4. Maximum of 4 and 5, 5. Maximum of 5 and 6, 6. And maximum of 5 and 6 is 6. So that's going to be the final answer. So let's see if this works. Okay, wait a minute. You see, this is a problem with making really long variable names. You just forget some stuff. Okay, so that works. So yeah, that's now let's just submit. And let's see. There we go. So that is the solution for this question. So does anyone have any questions on any of these last questions that I've done? And also on this one as well. Does anyone have any questions, any critiques? Maybe want me to explain something over again? Okay, so let's see. There's actually, yeah, that was actually the last problem. So in terms of that, we're pretty much done. Like I had mentioned, we have the GitHub here, so we have our solution. So if I just go over there, we have some of the previous questions, and we have the ones we just went over. So let me just open these up. So yeah, we have the commented code. So this is not the exact code that I wrote. I just wrote it, or I just wrote what the things you guys just saw like from scratch. But the code is going to be a little different from what I wrote here. You can look back either to this code or to the code that I just wrote in the video when we release it. But I did leave commented code and then also uncommented if you prefer that. So yeah, that's for the Max Island question. Same thing for the binary search tree question and for the other question. And yeah, I try to make it as readable as possible because my regular code is a lot less readable when no one else is looking at it. So yeah, I try to make it as readable as possible. So yeah. And last thing to touch on. So yeah, I'm actually gonna add this into the Discord in a second if you guys are curious. And yeah, thank you guys for coming. If you guys could please leave some event feedback and also join the Discord if you haven't, that would be great. So I'll just leave this up here for a few seconds before we close out. But thank you guys for coming. If you guys have any suggestions for any upcoming or for any workshops we can do in the future, definitely let us know in the Discord or maybe in the event feedback. And yeah, have a good night, guys. Sure, no problem, Layla. No problem, Felipe.